Hello, everyone, and welcome to our Spark AI session on adaptive query execution, speeding up Spark SQL at runtime. My name is Marianne, and I'm a software engineer from Databricks working on Spark SQL. I'm also a PMC member of the Apache Calcite and Apache Phoenix project. Today is going to be a 60-minute co-presentation by me and my fellow speaker, Ke from Intel. We'll start with what is adaptive query execution, also known as AQE, why is AQE, or the motivations behind it, and followed by a high-level introduction to AQE's framework and workflow. Then we take you through the major optimizations of AQE in Spark 3 using query examples and explain the technical details of how each of these optimizations work. In the second half of this presentation, my co-speaker Ke is going to do a live demo of all these AQE features to show the changes AQE makes to the query plans, and more importantly, how these changes accelerate the queries. Then she will present the TPC-DS benchmark result of AQE in Spark 3. Last but not least, she will also share Intel's customer experience with AQE in production. Adaptive query execution has been a well-studied problem in database literature. Spark first implemented this idea in version 1.6, but with rather limited functionality and extensibility. The Intel Big Data team later prototyped and experimented with a more advanced version of AQE and then worked with Databricks together to improve and ship this version in Spark 3. What exactly is adaptive query execution? Simply put, AQE is a query optimization, or to be more accurate, re-optimization that occurs in query execution. Unlike traditional query optimizations, which is conducted based on pre-collected statistics before query starts, AQE is a dynamic process of query optimization that happens in the middle of the query execution, using runtime statistics as its optimization input. In other words, AQE adapts and adjusts the query plan according to the actual characteristics of the data it discovers at runtime. Now the question is, why do we need AQE, or what are the challenges that AQE aims to tackle? Spark has had a cost-based optimizer since version 2.2, which tries to pick the best plan based on the input size and cardinality estimate. But the problem is when pre-collected stats are out of date or the desired stats are not even available, the estimate can become inaccurate, and as a result, Spark compiler might end up generating less optimal query plans. On the other hand, collecting comprehensive stats and keeping them up to date can be an expensive thing to do as well. So users often have to struggle between the overhead of stats collection and the accuracy of cardinality estimate. But let's say you're fine with all this overhead, or your dataset doesn't change as often. So you always have the most complete and up-to-date stats. And would you be free of all these problems? Unfortunately, no. Some predicates are just hard to estimate using stats. For example, predicates containing user-defined functions can be very much just like a black box, making selectivity or cardinality estimate literally impossible. Some users may try to rely on optimizer hints, but they do not always work either, especially with rapidly evolving data where previous assumptions of the data characteristics might not hold for the latest dataset. That's why we want to introduce you to AQE, which is targeted at solving these issues by basing optimization decisions on accurate runtime statistics. As AQE happens in the middle of query execution, one might be curious what's the timing of AQE performing optimizations and adjusting query plans? Or in other words, or at which exact point does this happen? To answer this question, let's first look into the execution flow of Spark operators. Spark operators are usually executed in a completely distributed and pipeline fashion except exchange operators like shuffle or broadcast. Shuffle or broadcast exchanges break the pipeline and divide a query into query stages. One query stage usually maps to a Spark job or Spark stage. At the end of each query stage, intermediate results are materialized on disks so that it can be copied and transferred across the network to form a new distribution as required by the next query stage. Because of this inherent property of being the pipeline breakpoint and a materialization point, we choose query stage boundaries as the time when AQE performs runtime optimizations. This means zero disruption to the existing execution flow, and also it's one of the easiest places to get runtime statistics, both dataset-wise and partition-wise. The query from the right-hand side example contains two query stages. The operators scan and partial aggregate in the first stage run in distributed parallel tasks. And at the end, the shuffle materializes the stage's output onto disks, partitioned in a way that records having the same group by key co-located in the same partition. The second stage then starts with parallel tasks to read partition output from the first stage to form a new distribution. The final aggregate from the second stage now operates on this new distribution before the following shuffle materializes the output again, partitioned on the order by key this time. Both of these shuffle materialization points from the first stage and the second one are going to be where AQE jumps in and tries optimizing the query plan based on the statistics returned from these shuffles. Now, by putting things all together, we can get this workflow of dynamic query execution. The very first step is to kick off all leaf stages, which means stages that do not depend on the input of any other stages. Then we wait for any of the running stages to complete, which then trigger AQE's next steps. Because as soon as one or more stages are done, it means two things. First, that part of a query has runtime statistics coming in and can provide new insight for AQE optimizations. Second, some other stages that are dependent on the finished stages may now have their dependency requirements satisfied and are ready to be started. So the next two steps are one, to run the optimization and update the current query plan, and two, start the query stages with dependency cleared. We keep repeating these steps of performing optimizations and starting new stages whenever a running stage finishes. It brings AQE process to its end once all the stages have been completed. Now that we've gone through AQE's framework and workflow, we'll introduce the three major optimizations AQE has implemented in Spark 3. First one is the dynamic coalescing or combining of shuffle partitions. Second one is join strategy switching, basically from sort merge join to broadcast hash join. And the last one is the dynamic skew join optimization. Let's first look at the dynamic coalescing of shuffle partitions. Shuffle exchanges often have a big impact on query performance, and getting the right partition number is what gets you the best shuffle performance. For example, over-partitioning can make partition sizes too small, and Spark jobs will end up with more frequent and inefficient IOs and higher latencies because of the scheduling and task setup overhead. On the other hand, though, partitions being too large usually leads to more serious problems, as there will be greater memory pressure in each task. And if it goes beyond the limit, Spark operators will resort to disk billing, and that slows down the query even more. It is often, though not always, the result of under-partitioning, which means your query works with a large data set, but the partition number is not scaled up to match the data size. And then what makes tuning the partition number even more difficult is the fact that the data size changes at different points of the query execution. Some operators, for example, filter or aggregate, bring the size down, while other operators like join can blow it up, which means you can't cater to all parts of the query with just one partition number. But unfortunately, Spark uses only one such number for the entire query. And that's why AQE does this dynamic coalescing of shuffle partitions. So you can start with initial partition number big enough to accommodate the largest data blow point in your query. and then rely on AQE to coalesce the partitions after each stage, suiting the partition number to the actual data size as it changes throughout the queries. Let's use this example to understand when and how the query plan is changed by AQE's partition coalescing. This is the same example we used earlier to explain the idea of query stages. In this query, we select from table T and group by column X, and then in the end, order by aggregate expression average Y. An initial plan comes out as a partial aggregate on top of a table scan, followed by a shuffle on the group by key. Then there's a final aggregate, followed by another shuffle on the order by key. And finally, the sort. We set the initial partition number as 50, so each shuffle operator here has partition number 50. As mentioned earlier, we'll first start and run leaf stages, and in this case, it's the shuffle stage on the bottom containing the partial aggregate in the scan. Once this stage is complete, we can see that the overall data size is 650 megabytes, with each partition averaging around 13 megs, which is a little too small. So the AQE optimizer figures those partitions can be coalesced to 10 bigger partitions instead. As a result of the first round of AQE optimizations, we can see that the new execution plan is now added with a coalesce node on top of the first stage. Next, we figured that stage 2, containing the final aggregate, can be triggered. Meanwhile, the coalesce node in the new plan means the second stage will start with 10 tasks instead of the statically planned 50. Now, as stage 2 finishes, we see that the partition sizes, being 6 megs on average, are even smaller after the final aggregate. Again, AQE applies a new coalesce node on top of the second stage with only 5 partitions. At this point, AQE is done with its job. As we can see, all the query stages have been completed. The rest of this query will now run with 5 parallel tasks based on the latest plan generated by AQE. Next, let's take a peek inside this coalesce operator and see what it does to decrease the number of shuffle partitions. This is what a regular shuffle process without coalescing looks like. For simplicity, we just use 5 as the initial partition number and assume there's only 2 map tasks. The first step of a shuffle is the map side partitioning based on partition keys. Since our partition number here is 5, the partition keys will be hashed into 5 different groups, and the 2 map tasks here partition their data into 5 sections corresponding to each key group. The second step of a regular shuffle is to have one reducer for each key group, and each of these reducers will read data belonging to their respective key group from all the mappers. So on the right-hand side of this diagram, you can see that reducer 1 reads all the data from the first key group, which is marked red, and reducer 2 reads data from the second key group marked purple, and so on and so forth. Now, this is what a coalesce shuffle looks like. The first step, the map side partitioning, remains exactly the same as that of a regular shuffle, but the difference lies in the second step. It is obvious that adjacent partitions corresponding to key groups 2, 3, and 4 are small partitions, so that's why we have a coalesce operator to combine them here. Now, instead of setting up 5 reducers for each key group, the coalesce shuffle combines data from key groups 2, 3, and 4, so that there is now only 3 reducers, with reducer 2 reading from the initial partitions 2, 3, 4. Operators that follow this coalesce node in the same query stage will in turn run with 3 partitions instead of 5. Now let's come to our second AQE optimization today, the dynamic join strategy selection. We all know that broadcast hash join runs faster than the sort merge join, and that's why Spark picks broadcast hash join over other join strategies if one side of the join is small enough to fit well in memory. But like we said earlier, the estimates can go wrong for a number of reasons. For example, missing or stale stats, hard to predict predicates, etc. For Spark join strategy selection, that means the opportunity of doing broadcast hash joins can be missed sometimes. AQE tries to remedy this situation by switching over to broadcast join at runtime once the query stage from either side of the joins finishes with a data size that falls below the broadcast threshold. This is an example of how dynamic join strategy switching works. This example query has a photo on one of the join tables, and it's hard to get a good estimate on the selectivity of that photo. And for this reason, the Spark static planning picks the sort merge join. As AQE starts, we have two leaf stages in this case, so we start both of them at the same time. The second stage turns out to be rather small and finishes quickly. The estimate was 25 megabytes, but the actual size is only 8 megabytes, which goes below the default broadcast threshold 10 megabytes. The completion of this stage triggers AQE optimizations in which AQE changes the query from the originally planned sort merge join into a broadcast hash join. As we can see in the new plan that shows up in the second step here, the sort operators have been taken away. And meanwhile, there is now a new broadcast query stage, which is to be kicked off right afterwards in the third step when we start the next batch of stages that are ready for execution. The third and last AQ optimization we talk about today is the dynamic skew join handling. Data skew is a problem when data is not evenly distributed, leading to some partitions being much bigger than the others. This can cause significant performance downgrade, especially with sort merge join. Those individual long-running tasks will become stranglers, slowing down the entire stage. And what is worse is that this spilling usually happens in those especially large partitions, doubling the effect of the slowdown. Well, thanks to the partition stats it gets after each stage, AQE is in a unique position to detect such skew. And once a skew is detected, AQE splits those skew partitions into smaller subpartitions, which eliminates both the strangler and the spilling problem. This is how the skew join optimization happens in the AQE workflow. Similar to the previous example, this is a join query planned as sort merge join. Both stage 1 and stage 2 are leaf stages and are started simultaneously in the first step. When stage 2 finishes, no optimizations can be applied and the plan stays the same. And when stage 1 finishes, it shows an apparent skew by having one partition of over 250 megabytes of size and the others around 55 megabytes. This triggers the skew join optimization, which adds a skew shuffle reader on both sides of the join. The next two slides will explain what a skew shuffle reader does and why the non-skew side also needs such a skew reader. First, this is how a regular sort merge join without skew optimization works. Again, for the purpose of simplicity, we use 4 as the initial partition number here. Both join tables, table A and table B, will first be partitioned on the join key, and the partitions that fall in the same key group will be sorted and then joined together in their respective tasks. For example, in a diagram here, partition A0 from table A will be joined to partition B0 from table B, and partition A1 joined to partition B1, etc. The problem here with A0 being especially large is that it will take the first task a much longer time to complete than the other 3 tasks, which slows down the whole query. Now, in order to solve the skew problem, skew join optimization splits the skew partition A0 into smaller subpartitions so that each task containing the new subpartitions now deals with the input of a smaller size and can avoid this spilling. After the split, A0 now becomes A0-S0, A0-S1, and A0-S2. Each of these new subpartitions need to be joined with partition B0 respectively to ensure we still get a correct result after changing the partition layout of table A. In order to do that, we create 3 duplicates of partition B0 to match the new partitions from table A. And that is why we need a skew reader for the table B side, even though it does not have a skew itself. After this skew join optimization, the SORMA join now runs with 6 partitions up from the original 4, which means a more balanced load and no dispilling, and more importantly, a speed up of the query. All right, this is the end of my part today, and you must be excited to see how AQE works in a real cluster. So let me hand it over to Ke, who is going to give you an awesome AQE live demo.
Firstly, we need to enable AQE. It is disabled by default, and you can use the umbrella configuration of Spark SQL Adaptive Enable to turn it on when you decided to use AQE features. We can click the right button to execute the circle. Okay, the circle is done, and we have already enabled AQE in this demo. Secondly, we need to create 2 tables and prepare the test data for this demo. The first one is the item table with ID and price 2 columns. The second one is the sales table with ID, quality, and date 3 columns. In order to show the performance of dynamically optimizing school join, the sales table is school, with the most 80% 100 value in item ID column. Here, I have already prepared the test data for the 2 tables, so we don't need to generate data again. Okay, let's begin the first feature, dynamically coalescing shuffle partitions. Here, the test circle is to get the sum of sales quality grouped by sales date. In order to show the performance both enabling and disabling QE, we also run the circle without AQE features previously. And because the execution time is long, so we only show the execution result and we will not run the circle without AQE in this demo. Generally, Spark set 1 common partition number for the whole query stage, regardless of the amount of dataset changes. Then, when the dataset is very small, after filter or aggregation, the performance will downgrade. If with a too large partition number because of the task schedule and startup overhead. Here, in order to demonstrate the overhead, we set the shuffle partition numbers to 10,000. And we can see the execution time when disabling QE is about 14 seconds. How much time it will cost when enabling QE? Okay, let's begin the circle with the QE. And before the start, we set 3 configurations for this feature. Of course, the first one is to enable QE, and the second one is to be same with the disabling configuration with 10,000 shuffle partition number. And the last one is to set the mean partition number to 1 because the data size after aggregation is very small in this demo. You don't need to set it to 1 in your real use case. The default value is the parallelism of Spark cluster you used. Okay, let's run this circle. The circle is done. And we can see the execution time is very short, only about 3 seconds, which can gain about 4 times performance improvement compared without AQE in this query. Then we can go to the Spark UI to see the change in query plan. Hold on a moment. Then we can go to the circle tab. Okay, the query plan is coming. We can see this query is simple. It firstly scans the sales table and then executes the aggregation operator. Here we can see the exchange node after the aggregation is only 700 kilobytes, which is very small. So AQE will combine the smaller partitions into a new partitions to execute the shuffle operator in this query, which means there will be less IO request and the schedule overhead. This is the demo for coalescing shuffle partition number. Next, let's go to the second feature, dynamically switching the join strategies. For the second feature, the test circle we used is to get total sales amount grouped by sales date for items with a price lower than 10. Similar with the above run approach, we also run this circle without AQE features to compare the performance with AQE. Here we can see the execution time is very long, about 7 minutes. And we can go to the Spark UI to see the query plan without AQE. Here I have already opened the query plan earlier. The circle firstly scans the table sales and item, then join the two tables with summary join. And we can find the exchange node of item table after scan, and the filter is very small, only 3.3 megabytes. But Spark applies the join to summary join in planning stage, because Spark uses the estimation data size to plan the query in static phase. And sometimes the estimation may be wrong with some reasons. So the summary join is chosen to perform the join operator, which causes the performance fall due to the heavy shuffle operator overhead. What will change in runtime when we enable AQE? Okay, let's go back to the circle with AQE and find the changes. Okay, let's run the circle with AQE. The circle is running. We can hold on a moment. The circle is done, and we can see the execution time is only 31 seconds, which can gain about 13 times performance improvement compared without a QE in this query. Next, we can go to the Spark UI to see what changes make a hugely improvement when you import a QE. Okay, we can see the biggest change is that Spark switches the sophomore join to broadcast hash join. Because when you import QE, Spark will re-optimize the query plan based on the real data size. And when one join size is smaller than the broadcast hash join threshold, Spark will pick the broadcast hash join to perform the join operator. And we know the data size of item table after filter is only 3.3 megabytes. So the join is optimized to broadcast hash join when import QE, which can read the shuffle file locally to reduce the network traffic overhead. This is the demo of dynamically switching join strategies. At last, let's go to the feature dynamically optimize the school join. Here, the test circle we used is to get the total sales amount grouped by sales date. And the partition in the sales table containing value 100 as the item ID is much larger than other partitions. When disable QE, the execution time is very long because of the school use case, which can seriously go down the performance due to the longest task. And we have already executed this query without a QE previously. We don't need to run it again. And the execution time is about 7 minutes. Then let's go to run this circle with a QE and see how much time it costs and when you import QE and how Spark resolves the school issues in runtime. The circle is running, and we can hold on a moment. The circle is done, and we can see the execution time is only 48 seconds, which can gain about 8 times performance improvement compared without a QE in this query. Next, we can go to the Spark UI to see why importing QE can gain the improvement. Okay, we can see the circle is to join the table of sales and item after scan and filter. And because the table of item after filter is is about 352 megabytes, which is bigger than the broadcast hash join threshold. So the query cannot be optimized to broadcast hash join. And we know the table of sales is school earlier. And when you enable AQE, Spark will detect the school partition. Spark will detect the school partition and then split the school partition from one big partition into 32 smaller partitions in runtime. We know the school join is due to the longest task make the whole query slow. And after the splitting, all the evenly sized tasks can make almost same execution time. Then the school issue can be resolved. Okay, this is the part of lab demo. At last, I will show you the performance of AQE in TPC-DS and production. Finally, let me show you the performance result in TPC-DS and the production. Here is the cluster setup for test environment in 3 terabytes TPC-DS. In our test, we have 5 server nodes with the Intel Castlake CPU. It has 96 cores and 384 gigabytes memory and 7 SSD. And the network is 10 gigabytes. And we run the Spark master with the commit ID 0B6AAE. Okay, we run the TPC-DS with 3 terabytes in our benchmark and compare the performance with Spark Circle and adaptive query execution. And we found many queries gain the performance improvement. The best 2 queries can gain over 1.5 times improvement. And most 37 queries can gain over 1.1 times improvement. And when we analyze the queries in more details, we can see why we get the performance improvement. The first one is dynamically coalescing shuffle partitions. And we pick the query 8 to show the performance improvement. Initially, we set a large partition number with 1,000. In this query, we can see that we have 2 stages. The data size is not very large, and the execution time is separately 5 seconds and 11 seconds. And with AQE mode, Spark can dynamically coalesce the shuffle partition number to about 700. And the execution time can be 2 seconds and 6 seconds, which can gain about 2 times performance improvement. Because this means we have less schedule overhead and the less task startup time. And it also means there will be less disk I/O request because we combine the continuous partition into one single request. And we also observed that the data shuffle write to disk is also less after the aggregation. So in this case, we get the performance improvement by dynamically coalescing shuffle partitions. This feature simplifies the tuning of shuffle partition number when running queries. and you don't need to set a proper shuffle partition number to fit your dataset. AQE can pick the proper shuffle partition number at runtime once you set a large enough initial number of shuffle partitions. The second feature is dynamically switching join strategies. Here I list the example with query 14b. When without AQE, Spark picks the short-merge join to join the two tables in planning phase because of the wrong estimation data size. So in this query, the stage took a long time to finish the joins because of the shuffle operator overhead, and it total takes about 13 minutes. When enable AQE, Spark can get the real data size in runtime. Then AQE will re-optimize the short-merge join to broadcast hash join when one join set data size is smaller than the broadcast hash join threshold. We can see from the image that the one join set is only about 10 megabytes, which can fit in memory. So Spark optimizes the short-merge join to broadcast the join in the runtime. And after the optimization, the stage only cost about 3 minutes to finish the join, which improved about 4 times when enable the feature of dynamically optimizing join strategies. This feature can read the shuffle file locally to save the network traffic and also change the random read to sequence read. Because the data generated in TPC-DS is much evenly, and we don't gain the performance improvement with the dynamically optimizing school join features in 3 terabytes TPC-DS. But AQE can gain improvement by resolving the school join issues in real workload. Here is the result shared by two big companies in China. The first one is shared by one of the largest e-commerce companies in China. AQE helped them resolve the critical data school issues and achieved significant performance for their online business queries. And the best one can gain about 18 times in their production environment. The second one is shared by one of the largest internet companies in China. And AQE can achieve 5 times performance improvement in their online environment. We also analyze the one school queries in their online environment. The circle is to select the user's invoice detail based on the sales order ID, invoice content ID, and the invoice type ID. The execution time of those circles is very long when without AQE. After detailed analysis, we found the join key of the sales order ID, invoice content ID, and the invoice type ID all contain the school partitions. For example, the average record of sales order ID without NULL value is almost 2,000. However, the school records with no value can be up to 15 million records, which causes seriously school join issues in their query. When you import AQE, Spark will split the good partitions into more small partitions. Then those tasks will take roughly the same execution time, which can accelerate the whole query. And we can see the best one can gain about 18 times improvement. This is my part about AQE demo and performance both in TPC-DS and production. Okay, thanks everyone for listening the demo for AQE. And do you have any question?